Hello students, welcome to EPG Pathshala. I am Dr. Varun Vyas from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Transducers Part 2 from the paper Measurements and Instrumentation. In this module, we will focus on various types of resistive transducers. Here we will study about principle of operation of an resistance gauge, resistance thermal detectors RTD, thermal thermistor, that is thermally resistive transducer. In this module, we will look at transducers. As discussed earlier, a transducer is a device that can convert energy or information from one form to another. In a measuring system, the transducer or combination of transducer act as input element. They play a critical role in transforming some physical quantity to a proportional electrical signal. Therefore, selecting an appropriate transducer is important to get accurate results. While selecting a transducer, first step is to understand the nature and quantity under measurement with known range of magnitudes and frequencies to be expected from the measurand. Thereafter, one should examine the available transducer for, for the principle of measurement for the desired quantity. Transducer once identified for a measurement should be compatible with the type and the range of quantity to be measured and the output device. There are various types of transducers: active, passive, sensors, actuators, etc. One should always be aware of inverse transducer. It is a device that can convert an electrical quantity into a non-electrical quantity. They usually are precision actuators that have an electrical output and low power non-electrical output. Many data indicating and recording devices are inverse transducers. Many analog measuring instruments like ammeters or voltmeter convert electrical current into mechanical movement in the measuring dial. Resistive transducer. A resistive transducer belongs to the category of passive transducer. Here, the resistance between the output terminals of a transducer gets varied according to the measurand. A resistive transducer is preferred over other transducer. This is because they can be used in both AC and DC circuits for resistance measurement and for any metal conductor. The resistance here is given by R is equals to rho into L by A. This is equation 1, where rho is the resistivity of the material in ohms meter, L is the length of the conductor in meters, and A is the cross-sectional area of the conductor in meter square. For a physical phenomena, an input signal to the transducer leads to changes in any one of the above mentioned quantities, that is rho, L and A. For any conductor or semiconductor, any variation in force or pressure leading to change in resistance is measured via strain gauge. Changes in the resistance due to variation in temperature can also be recorded by a resistive transducer. Variations in light intensity, that is for photoconductive effect, changes in resistance can be easily recorded, and same is for magnetoresistive effect, where changes in the magnetic field can be observed by measuring resistances. For various measurements, primarily resistive range is in the mid-range of 100 ohms to 100 kilo ohms. Strain gauges. A strain gauge is a device that is used for measuring mechanical surface strain and is one of the most extensively used electrical transducers. It can detect and convert force or any small mechanical displacement into electrical signal. Mechanical displacement with time-varying form with frequencies up to 100 kHz can be detected with this device. Based on the application, the strain gauges can be classified into two areas. First, the primary objective of the gauge is measurement of strain of machines and structures. Second, the measurement of strain due to other parameters such as load, pressure, acceleration, and other force associated variables. Based on the operating principle, gauges can be classified into mechanical, optical, and electrical. Mechanical gauges are used for measuring static strain only. Their application can also be extended to those measurements that can be conducted by visual means. Optical strain gauge is similar to mechanical, only difference being that magnification is achieved via multiple reflectors, that is mirrors and prisms. Its accuracy of measurement is high and is independent of any temperature variation. In electrical strain gauges, measurement is based on changes in resistance, capacitance, or inductance that are proportional to the strain transferred from measurand to the gauge element. Operating principle of resistance gauge. Credit towards the development of electrical resistance strain gauge goes to Lord Kelvin. In mid-19th century, he expounded the theory of copper or iron wire tend to change the resistance when they are subjected to tension or compression. This change in resistance of conductor under stress also alters the resistivity of the conductor. This effect is also known as piezo-resistive effect. Therefore, strain gauges are also called piezo-resistive strain gauges. As discussed earlier, the resistance of the unstrained gauge is given by equation 1. Under strained conditions, let us assume resistance changes by delta R, length changes by delta L, cross-sectional area changes by delta A, and resistivity by delta rho. These four quantities can be expressed by differentiating equation 1, and we get delta R divided by delta rho, which is equals to delta divided by delta rho multiplied with rho into L by A. This is equals to rho by A into delta L divided by delta rho minus rho into L divided by A square into delta A divided by delta rho plus L divided by A into delta rho divided by delta rho. This is equation 2. Dividing both sides of the expression by R and by taking into account small variations, the above expression can be written as delta R divided by R equals to delta L divided by L minus delta A divided by A plus delta rho by rho. This is equation 3. Under strained conditions, cross-sectional area also changes, so the diameter of the conductor will also change. The area is equals to pi by 4 into d square. By differentiating the above expression and dividing both sides by A, we get 1 by A into delta A divided by delta S. This is equals to 2 pi by 4d divided by pi by 4d square multiplied with delta d divided by delta S. This is equation 4. For small variations, delta A divided by A is equals to 2 delta D divided by D. This is equation 5. And changes in the diameter will also lead to change in the length of the wire is given by Poisson's ratio mu for the given wire material. Delta D by D is equals to minus mu delta L by L. This is equation 6. For most materials, the value of Poisson's ratio of 0.3 is considered. From equation 5 and 6, we get delta A divided by A is equals to minus 2 mu into delta L by L. This is equation 7. By substituting the above expression in equation 3, we get the expression for the gauge factor. The gauge factor is equals to delta R by R divided by delta L by L. This is equals to the first term 1, that is change in resistance due to change in length, plus 2 mu, that is change in resistance due to change in area, plus delta rho by rho divided by delta L by L. This is change in resistance due to piezoresistive effect. This is given by equation 8. The gauge factor G gives the strain resistivity of the gauge in terms of change in resistance per unit strain. Third term for the resistance due to piezoresistive effect can also be expressed as pi E, where pi is called longitudinal piezoresistive coefficient and E is called modulus of elasticity. Resistance temperature detectors RTD. Resistance temperature detectors are also known as resistance thermometer. They are electrical transducers that enable measurement of resistance changes in terms of resistance change. The resistive element is made up of solid material, a metal, a metallic alloy, or a semiconductor compound. The resistivity of the metals increases with temperature, whereas for semiconductors and insulators it generally decreases. Electrical resistance with temperature for various metals is expressed by the following equation. RT is equals to R naught multiplied with 1 plus alpha T plus beta T square plus gamma T cube plus omega T raised to power n. This is equation 9, where R naught is the resistance in omega at reference temperature point, that is ice point of 0 degree centigrade. RT is the resistance in omega at temperature T. Alpha is the temperature coefficient of resistance in omega by degree centigrade, and beta, gamma, omega are coefficients determined on the basis of 2 or more known resistance temperature points. For narrow range of operation, beta and other higher terms become negligible, and expression 9 can be written as RT is equals to R naught into 1 plus alpha T. This is equation 9. The RTD can be used for measuring small temperature differences as well as for wide range of temperature. The main drawback of this instrument is its large size and sophisticated instrumentation. The requirement of resistance material in resistance thermometers are: first, high temperature coefficient of resistance to give noticeable change in resistance for small change in temperature, that is, large sensitivity. Second, the high resistivity for small wire length for high resistance. Third, linearity of relation between resistance and temperature. Fourth, stability of electrical characteristics of material, which is essential for good repeatability. And 5, good mechanical strength so that very fine wires can be drawn for reducing response time and gives adequate ruggedness in the construction of device. Platinum is the most preferred material in laboratory work and industrial measurements of high accuracy. Platinum is commercially available in pure form and is relatively stable under different environmental conditions. Its resistance curve is simple and holds true over a wide range of temperatures, that is, minus 163 degrees centigrade to plus 545 degrees centigrade, that too with high precision. Its resistivity increases less rapidly at higher temperatures. At the same time, it maintains an excellent stability. The common value of resistance of a platinum RTD ranges from 10 ohms for a birdcage model to several thousand ohms for a film of RTD. The common value of 100 ohms is at 0 degrees centigrade with the temperature coefficient of 0.00391 per degree centigrade. Theory. For the sake of simplicity, expression 10 can be written as RT is equals to R0 multiplied by 1 plus KT. This is equation 11, where K is the fundamental constant whose value is determined by measuring resistance at 0 degrees centigrade and 100 degrees centigrade. If R0 and R100 are resistance measured at 0 degrees centigrade and 100 degrees centigrade respectively, then we get the following equation. R100 is equals to R0 multiplied by 1 plus 100K, or K is equals to R100 minus R0 divided by 100 R0. This is equation 12. The above equation gives the value of K. Then the resistance R at temperature Tp degrees centigrade is given by the following expression. RT is equals to R0 into 1 plus K Tp, where Tp is the temperature of the platinum. The above equation can be written as Tp is equals to 100 into RT minus R0. This term is divided by R100 minus R0. This is equation 13. R100 minus R0 is the fundamental interval and is constant for a given temperature. Platinum resistance thermometer is coupled to Wheatstone bridge or Kelvin bridge depending upon the accuracy required and the range of measurement. The modified circuit for resistance thermometer is given in figure 1. Thermometer tube has 3 core cables. One forms the variable resistor, middle one from the galvanometer, and the third one has platinum resistance coil. The coil is in form of free spiral or is held by insulated carrier such as mica or ceramic. The diameter of the wire is 0.02 millimeter to 0.2 millimeter and the preferred thickness is 0.1 millimeter. Thermistor. Thermistors are thermally sensitive resistors. Resistance of a thermistor varies as a function of temperature. The thermometer element is made from semiconducting compounds. These compounds are sintered mixtures of sulfides, silicates, oxides, and selenides of metals such as nickel, manganese, cobalt, copper, zinc, iron, aluminium, and uranium. Depending upon their composition, the sensitivity may vary from 10 raised to power minus 1 to 10 raised to power 9 ohm centimeter. The resistance values of thermistor at 20 degrees centigrade may lie in the range of 100 ohms to 1 mega ohm. The elements are in form of beads, rod, disc of various sizes. The beads and disc are available with glass envelope capsulation. The bead may be small as 0.1 millimeter in diameter and may have resistance as high as 10 kilo ohms. Thermistor disc range from 2.5 to 25 millimeter and 0.5 to 12.5 millimeter in thickness, whereas rod type thermistor vary from 1.3 to 4.4 millimeter in diameter, from 6.4 millimeter to 51 millimeter in length. The material used thermometry possesses high resistivity and high negative temperature coefficient of resistance. Some compound mixtures have positive coefficient. The resistance temperature characteristics are nonlinear and are governed by relation RT is equals to R naught into exponential of beta into brackets 1 by T minus 1 by T naught. This is equation 14, where RT and R naught are resistance values of the thermistor at absolute temperature of Tk and T naught Kelvin respectively, and beta is the material constant expressed in degrees Kelvin. For commonly used material, the value of beta at 25 degree is 4000. The temperature resistance characteristics of thermistor materials is shown in figure 2. It is seen that thermistors are limited in their application as they can only be used for the range minus 100 degrees centigrade to plus 300 degrees centigrade. Some thermistors contain sintered aluminum oxide and are used up to 1000 degrees centigrade. They are quite useful for compensating electrical circuits for changes in ambient temperature. The merits of thermistor over wire resistance elements for temperature measurements lie in their high values of temperature coefficient, relatively small size for making localized measurements possible, low thermal capacity, high speed of response, and large resistance value. The time constant varies from 1 second to 20 seconds depending upon the protection tube, and when directly used it may go down to 100 milliseconds. In this module we studied about various types of resistive transducers. After studying about resistive transducers, we studied in detail about principle of operation of a resistance gauge. Thereafter, our objective was to study about resistance thermal detectors, that is RTD, and finally we studied about the theory and other basic fundamentals of resistance thermometers. In the end, we studied about the thermistors. They are also known as thermally resistive transducers. Thank you.